This is Pre-Calculus section 3.3 part 2 notes. I'm continuing on with example 3 where I left off in the previous video. Notice that I added this note over here that for my P over Q's for my new polynomial that they're plus or minus 1 and 2, but I already tried positive 1 and positive 2 in the original polynomial, and if they didn't work before, they will not work now. So that's why I started my synthetic division with negative 1. Okay, so I really only have one left to check, and that is negative 2. So let's find out if that is a solution. So I'm going to drop down my 1. Negative 2 times 1 is negative 2. 0 plus negative 2 is negative 2. Negative 2 times negative 2 is positive 4. Negative 5 plus 4 is negative 1. Negative 2 times negative 1 is positive 2, and negative 2 plus 2 is 0. All right, cha-ching. So I know that x equals negative 2 is another solution. And I also know that I have a new polynomial here, and my new polynomial is x squared minus 2x minus 1. Now, if you want to solve that, you could try factoring it. It looks like an easy factor, but you're not going to be able to find a pair of numbers that multiplies to make negative 1 and adds to make negative 2. So what that tells you is that our remaining zeros for this polynomial are not rational, okay? So if we want to solve this, we have to find our remaining solutions by the quadratic formula. Okay, so our x solutions would be the opposite of b, 2, plus or minus the square root of my b value, which is negative 2 squared, plus negative 4 times a, which is 1, times c, which is negative 1, all over 2 times my a value, which is 1. So now I simplify. This is 2 plus or minus the square root of, this is 4 plus negative 4 times 1 times negative 1 is 4. So 4 plus 4 all over 2, which is 2 plus or minus the square root of 8 all over 2. And square root of 8 can be simplified, right? You can break that apart into square root of 4 and square root of 2, and the square root of 4 is 2. So 2 plus or minus 2 square roots of 2 all over 2. And finally, I can reduce those 2's. I can divide them all by 2. So then I end up with x equals 1 plus or minus the square root of 2. So those are two more solutions, but those are irrational solutions. They are real. I did not get a negative under my radical, so I have 4 real zeros to this polynomial. They're positive 5, negative 2, and then 1 plus or minus the square root of 2. It's just that 2 of them are rational and 2 of them are irrational. The next thing we're going to talk about is Descartes' Rule of Signs. Descartes' Rule of Signs tells you about the nature of the solutions that you could have, whether they are positive or negative. So if p of x is a polynomial with real coefficients, then the number of positive real zeros of p of x is either equal to the number of sign changes in the polynomial or is less than that by an even whole number. Okay, so if you look at all the terms, we're talking about the sign changes from term to term to term. So every time there's a sign change, that counts as 1. And so you take the number of sign changes, and the positive real zeros is going to be equal to the number of sign changes or less than that by an even whole number. Okay, so right now, let's do an example to support that part 1. Okay, we've got this polynomial p of x, and we're looking at the sign changes in the polynomial. Okay, just as it is. So our 3x to the 6th is a positive term. Our 2x to the 5th is a positive term. Our x cubed is a positive term. And then our negative 5x is negative, and our constant term negative 1 is negative. So if you look, you can see here that all I have from here to here is 1 sign change. So what that tells me is that this polynomial has 1 positive real zero. Okay? Now, if it were bigger than 1, like let's say there had been 3 sign changes, then it would be either 3 or less than that by an even whole number. So it would be 3 sign changes, or 3 minus 2 would be 1 sign change. So obviously the bigger the number of sign changes, the more possibilities you're going to have. Now to find the number of negative real zeros, that's either what you're going to do is you're going to substitute negative x in for x and simplify to determine if the term is positive or negative. Then once you do that, you look for your sign changes again, and it's the same rule. It's either the number of sign changes or less than that by an even whole number. So for this same polynomial, okay, we're going to plug in negative x for x. So it's going to be 3 times negative x to the 6th plus 2 times negative x to the 5th plus negative x cubed minus 5 times negative x minus 1. And now we simplify. Negative x to the 6th is going to end up being positive. Negative x to the 5th is going to be negative. Negative x cubed is going to be negative. Now be careful here. Negative 5 times negative x will become positive, and then my constant term will stay negative. So now I have a sign change here, I have a sign change here, and I have a sign change here. So this is 3 sign changes. So that tells me that I have either 3 or subtract 2 from 3 and that gives me 1. So I have either 3 or 1 negative real zeros. Okay, so what you will commonly see, and sorry I don't have a lot of room to do this, I'm going to smush it in here. What you will commonly see is a little table here of possible positive real zeros and negative real zeros and total real zeros. Well, what I know about this polynomial is that it has 6 zeros, but I don't know if they're all real or if some of them are real and some of them are imaginary. That we don't know. So all we can work with is the information that we have. And what we know based on Descartes' rule of signs for this example is that for sure we have 1 positive real zero. But we could have 3 negative real zeros, or we could have 1 negative real zero. But the number of positive real zeros is going to be 1 no matter what. So that means that our real zeros, we could have 4 total, or we could have 2 total. And since there are 6 zeros, either 2 or 4 are imaginary. Okay? Let's do another one. Okay? So here we have a new p of x. Let's find our positive real zeros. So we have a positive term, we have a negative term, we have a positive term, we have a positive term. So we have a sign change here and a sign change here. That's 2 sign changes, which tells us that we either have 2 or 0 positive real zeros. For the negative real zeros, we have to plug negative x in for x. So this is going to be 2 times negative x cubed minus 5 times negative x squared plus negative x plus 1. And now we simplify. Negative x cubed is going to make this term negative. Negative x squared is going to become positive, but a positive times a negative 5, that's going to stay negative. And then this term is going to be negative, and this is going to be positive. So all we have here is 1 sign change, which tells us that we have 1 NRZ, 1 negative real zero. So our total zeros here then are going to be, if we make a table just like we did before, we've got our positives, we've got our negatives, and we've got our total. So our positives were either 2 or 0. Our negatives were 1, 1 and only 1, right? So this would make our total real zeros here 3, okay? And this one would make our total real zeros 1. Now keep in mind that since this problem has 3 zeros total, or I should say this polynomial, either 0 or 2 are imaginary. So again, Descartes' rule of signs helps you figure out the nature of the solutions, of your real solutions. Are they positive or are they negative? Just another tool to put in your bag of tricks as you are trying to find all of the solutions to a given polynomial function. The last thing that we're going to talk about in this section is the upper and lower bounds theorem. This is the section that never ends. The upper and lower bounds theorem goes like this. Let P be a polynomial with real coefficients. If we divide P of x by x minus b, with b being greater than 0 using synthetic division, and if the row that contains the quotient and the remainder has no negative entry, then b is an upper bound for the real zeros of P. If we divide P of x by x minus a, with a being less than 0 using synthetic division, and if the row that contains the quotient and remainder has entries that are alternately non-positive and non-negative, then A is a lower bound for the real zeros of P. And there's a little asterisk here. The phrase alternately non-positive and non-negative means that the signs of the numbers alternate, with 0 considered to be positive or negative as required. Okay? So for our very last example, we're going to show that a equals negative 3 and b equals 5 are upper and lower bounds for the polynomial. Okay? So if we do synthetic division, again, let's do a quick check here. X to the fourth, x cubed, x squared, x constant, we're good. Okay, so we don't have any missing terms. I'm going to go ahead and I am going to, just going to make my t-bar chart here. I'm going to put my coefficients across the top. So I've got 1, negative 2, negative 9, positive 2, and positive 8. I want to show that negative 3 and positive 5 are upper and lower bounds for the polynomial. Okay, well, obviously positive 5 is going to be hopefully our upper bound, right? So let's check that. If we do positive 5, and again, we're just going to do synthetic division here. Drop down the 1. 5 times 1 is 5. 5 plus negative 2 is 3. 5 times 3 is 15. 15 plus negative 9 is 6. 5 times 6 is 30. 30 plus 2 is 32. 5 times 32 is 160, plus 8 is 168. Okay, so what I found here is no negative entry. So that tells me that positive 5 is an upper bound. Okay, now let's check the other one to see if it's a lower bound. Okay, so when I do negative 3, bring down the 1. Negative 3 times 1 is negative 3. Negative 2 minus 3 more is negative 5. Negative 3 times negative 5 is positive 15. Negative 9 plus 15 is 6. Negative 3 times 6 is negative 18. Negative 18 plus 2 is negative 16. Negative 3 times negative 16 is positive 48. Positive 48 plus 8 is positive 56. Okay, so these entries alternate in sign. So that means negative 3 is a lower bound. And that's it for the upper and lower bounds theorem. It is that simple. Just do synthetic division to prove that you either get all positive entries, or I should say non-negative entries, and then do the lower bound and show that you get alternating non-positive and non-negative to show that it's a lower bound.